we can talk about. Two more points that Feynman himself mentions. Mathematics aims for general case theorems, as general as possible, he says. And then physics aims for very specific results. The physicist doesn't care about all the objects in the universe, Feynman says, but the physicist only cares about the situation in front of her or him. This situation, I can describe it by guessing, by deducing, by inducing, by whatever you want to do. Can I describe it faithfully? Yes, then I have done my job, irrespective of all those other phenomena happening over there. And you know, if you go to a lab, a proper lab, people take huge care in isolating that lab from the outside universe. They wear triple coats, they wear gloves, they wear masks, they bury it underground just to isolate all those variables. I only want to observe this one thing. I don't want to observe the entire of the universe. That's too complicated for me. I don't want to worry about all those. I want to isolate all of those so that I can observe this one thing that I really care about. That's my job as a physicist. Whereas, according to Feynman and many others as well, mathematics does the opposite thing. The more general the situation is, the more general the discussion is, the better for mathematicians. Okay, let's tackle that one. Let's see if that one holds. It's enough in my head to provide two counterexamples, one for the first and one for the second, just to show, just like we did previously, just to show that even though sometimes things work in that way, many other times things don't. For mathematics, I'm going to give you this dumb logic that I have created. If you are with me on slide 13, I'm going to define one variable only, x. I'm going to define one constant only, which is a. Okay? And then I'm going to set as an axiom, only one axiom, the dumbest logic you can think of, only one axiom, which is that a is entailed, and only one derivation rule, you can see it dr there, which says any variable entails a before that variable. Just a simple concatenation logic. And then what are the theorems? Well, a is a theorem because a is an axiom. And then from a and the derivation rule, I can deduce double a because a before the variable, and then if you substitute the variable x with a, you can get double a, and then you can get a triple a, and you can get quadruple a, and then you can continue this. You can continue generating theorems here. Any one of those, you can publish them and say, I'm a mathematician. This is completely fine. Either this is math or this is not math. If someone wrote this on a piece of paper, would you say this is math or not? I say this is math, because if it's not math, what is it? Is it not mathematics, the art of deduction and formal reasoning, etc.? This is it. You want something more complicated? You want more arithmetic? I can add all the axioms of piano arithmetic for you. You want set theory? Oh, by all means, we'll add it. But it's the same exact work. It's the same exact work. If this is the case, we are not discussing this. We're discussing the claim that mathematics always aims for the most general case, the most general theorem. But look at this example. This example is so specific, it's actually useless and meaningless. It's so specific. Can you think of one thing that you can apply this logic for? One thing, just one situation in the world, in your imagination, anything you can. It's so dumb, it's so useless, this logic that I have created. Where is the most general case? And you're going to say, oh, but this is a dumb theorem. This is a dumb logic that you created. The good mathematics is the general case one. I'm sorry, number one, who says who? Number two, all general results start as very specific. We just saw the example of Fermat's last theorem. It started with someone proving n equals 3, Fermat himself proving n equals 4. Sophie Germain adding 3, 5, 7, someone else adding whatever family of primes, someone else. They start as a specific thing, and then they walk to the general. And this is, of course, desired. This is always desirable, having one small result in my pocket that explains a lot of things. This is very reasonable to look for. But can I claim that the people who did the work for specific cases are not doing mathematics simply because mathematics always aims for the general case theorem? No, I'm not willing to make that claim. So even my dumb logic here qualifies. Is it not an art in deduction? Is it not formal? Is there anything here that is not defined? No. Same thing for all the other theories in mathematics. You want the general case? Of course, everybody wants the general case. But if you're working in a specific case, doesn't mean you're not doing mathematics. So this point is highly questionable here. This position by Feynman is, I find it odd actually that Feynman himself makes that claim. The other face of the coin, physics. Physics in Feynman's mind aims to describe very specific phenomena. Just give me the description of this one thing I'm observing. Don't bother about everything else. I have a rule here in physics, at least in the classical physics, right? But I'm sure we have physicists in the room here. I'm sure that all the other developments in physics cannot go away from this one, and we can have a discussion about this, why or why not. But we have a very simple rule here. So this is the action-reaction rule, third rule of Newton. Whatever force is applied from A to B, there's an opposite and equal force applied from B to A. And this is kind of, if you want to think about it, one of the axioms, one of the definitions, one of the whatever that Newton does. Either you can think of it as a theorem that could be deduced, or you can think of it as an axiom. Not my discussion now. My discussion is on that specific point. Is this a specific description of a physical phenomenon, or is it the most general thing you can think of? This law, does it apply to one kind of forces, to one force in particular, to one experiment in particular, as Feynman posits that physicists always like this? Or does it have a more general, the most general form of validity, let's say, of description? This is used everywhere. There's four fundamental forces, classically speaking, in the universe, and all of those forces, they obey this. And then you can derive more families of forces. Let's say, contact forces, they're kind of a version of electromagnetic. Whatever, it's a version of the, you know what? You can always add more or less forces to that set. But all I'm saying is this rule applies to all of them. Is this not a general result? This is the most general you can think of. So again, the point that he makes that physics only cares about particulars and then mathematics always cares about the general is not always the case. I say generality and having a very general rule, just like we have F equals MA, or F of A over B is the minus of the other one. These are very nice to have, just like it's very nice to have a result about all real numbers or all complex numbers or all Hilbert spaces or all spaces in general or all logics in general, whatever. It's always nice to have one rule that describes many things. It's economic. We like these, whether it's in math or in physics. And we always, I shouldn't say always, but most of the cases, the vast majority of the cases, all of these general rules, they have started as very specific observations, whether it is in mathematics or whether it is in physics. Someone notices something, they wonder what is the scope of that observation, and then they start creating the necessary theoretical framework, whether it is in math or in physics, to kind of describe it and derive it. Questions? Or comments or whatever.
Well, so I mean, I'm still just struggling, the basic thesis here, because primarily because, I mean, unless it does get down kind of to the question of, does this stuff exist and we're discovering it, or are we just making it all up? And I guess I know this is kind of simplistic, but I'm thinking about, in math, we do make some postulates. That's all we can do. There's nothing you can do but make postulates, and then everything flows from them, with the exception of human fallibility, in a perfectly logical way. I mean, yes, I think the element of human fallibility does inject some interesting similarities, and it draws the question of what is consensus in both math and science. But ultimately, once you have decided on postulates, that's it. I'm saying you can't ask the question, are the postulates wrong? They're just postulates, and everything follows in a very certain fashion. There's no questioning any of that. Whereas in science, I mean, the example that you give, Newton's third law, is not a. I mean, it turns out there's all sorts of cases where you see it's violated, and then you see you can fix it by changing the definition of force or by doing something else. but fundamentally, the thing you wrote down was a guess about reality, and it can be falsified. I mean, it can really literally turn out that basic postulate is just wrong. And that's just not true in math.
Uh, I'm not sure whether I should reply from the physics point of view or from the math point of view. I think we will meet in the middle, but let me try from the math point of view first. There was a movement. Prime numbers have been an obsession for the entire history of mathematics. There was a movement to try to predict a formula for the primes, and it still exists for today. Like, people are hunting for this forever, and the current belief is that this is random. Until you find the formula, of course, the current belief is that excuse me, is that this is completely randomly distributed. When you say completely randomly, we have some idea that it is also not the case. So people have discovered that primes are becoming more and more scarce. So you have to go through a lot more numbers the larger the number is, so that you can find the second prime. One of those developments, it was Gauss and someone else, I forgot really the story now, but they have conjectured that, I think Gauss and Riemann, and then as a joint work, don't quote me on the story, but they have conjectured that prime numbers are approaching a certain limit of density. Okay, so it's always less than or equal than the log of n over n, or something in that order. I don't even remember the actual. It's not really important. And then the only way you can verify this, John, is not by doing some rigorous deductive proofing, whatever. The only way is, if you want to measure density, you have to have a big set of numbers and then divide the numbers you care about over the total. It turned out that it took a long time so that we can collect this. Of course, we didn't have computers, etc. And it was later on discovered that the actual number is above that limit that they did. So after like n equal 4 million or something, it goes above. But then they discovered that it goes below again. And then they discovered it goes above again. And then they discovered it goes below again after a certain n. And then the theoretical proof came that, oh, you know what? This is a limit at infinity, they converge. After that point. Okay? If you have a problem with that, how should I phrase this? That activity, in my mind, is the same exact activity that you are doing when you say, I don't have a proof in physics. When you say, I'm changing the definition of force, why would you change the definition to make a certain thing work out? Because of your personal preference, because you want this preference to help you deduce things. Right? You're kind of tweaking those axioms because you want to prove a certain thing. You're begging a certain result that you are observing. That Gauss and Riemann were also doing the same exact thing. You can tell me now, oh, they did not change the axioms. Oh, they didn't. But how did we get, for example, another branch of mathematics, which is non-Euclidean geometry? We changed an axiom. Is this making sense to you?
Yeah, right. And we're back to the example, right, of the twin prime conjecture or anything else. And I really do like that. I think within math itself, there is an activity that is like physics, like I described in physics. You make the twin prime conjecture, and it can turn out that that's just not true. That there is a place where you stop getting them or something, whatever the violation would be. So
And
that
that's enough.
is true.
Right?
Yeah,
And
no, you're
when
right.
we
I think
discover that's enough for us to, I don't even want a proof of the negation. You know what I mean? I just want that one specific counter example, and then I'm happy. Just like the same thing as in physics, the same exact thing.
well, I think you're right. I guess the difference is math starts with somehow there's a starting point that's different. The starting point of all the proof that the twin prime conjecture is wrong would start with an understanding that the rules of math are the rules of math, right? I mean, the fact that the conjecture is wrong stems from an acceptance of fundamental ideas in math that you don't get to question. Those are just you know, they can't be wrong. They can just be, not your preference to choose them. Whereas in physics, there isn't anything at the base. There's nothing at the base that you can be sure of.
I,
Nothing.
I wholeheartedly disagree with that. I think this is kind of not how to say. This is ungrateful of physics to say this about, because you guys owe the mathematical development quite a lot. When you say I don't have to assume anything, there's no base. Oh, the entirety of the body of mathematical theories is already assumed with you, plus the body of theories we will talk about in the future, which is the scientific method. How do we do observation? What is the correct way? What is peer review? How to do it exactly? So all these things are assumed, plus all the body of mathematical theories, or at least some of it. Let's not take the entire warehouse of mathematics. At least some of it that you really need, you already assume it for free. You don't go negate. You know what? Oh, let me see. Is this theorem that P is congruent to Q whenever PQ divides N? Is this valid or not? Oh, this is the mathematician's job. Let them check for the validity of that. I'm just going to use it for my own advantage whenever I need it. I've never heard a physicist say, "Oh, we're going to start questioning the proof of Hilbert spaces, whatever, whatever." Oh, no, they just take it and then they use it.
Well, we
They
don't
just take
ever
pi equal 3 and they don't care. That's what.
we don't
So,
ever worry that the mathematical part of what we do could be fundamentally wrong, in the same way that we know that the thing we're doing the math about could easily be fundamentally wrong.
well, I think it's as easy to make no sense with math as it is to make sense with math. It's just an expressive language. I can make sentences that have meaning. I can make sentences that don't have meaning. So I don't know what it means when John says they don't worry about getting the math right. I think people ought to be more worried about getting the math right.
No, and once again, I'm not talking about fallibility. I'm just saying that as physicists, we don't. Maybe we should more often. We do a proof. If we do the proof right within the model, right? We have a mathematical model. We can do proofs inside that mathematical model, and if we do that correctly, if we don't make a mistake, then the thing we come up with, we can test to see if it comports with reality. We don't
Well,
ever
I'm
work.
about your word because language suggests you get a Boolean result. In a proof framework, a thing either is or isn't. Um, but reality is rarely our confidence in our on our physics product is rarely Boolean. So when you say a physicist is using a proof, I'm worried already that he doesn't understand what the hell he's doing.
Well, I mean, once again, just remember, I'm saying we can do literal mathematical proofs within the model, which is a mathematical model of reality. It's not reality, it's a model
It's
that
that
we're
last
mapping
of
onto
reality that
reality.
gets you into trouble. Said, look, if you wanted to prove that the Earth was a globe, you would fail, right? The Earth is not a sphere,
Right.
right?
Well, okay. Oh,
That's
that's
what I'm
what you're
getting
saying.
at,
But I mean,
right? Like
I can,
reality
but I don't have to.
is you need to you could say something like this. The Earth is conformant with a sphere to 3 nines, right?
Right. And I don't have to
99.9.
prove that. I don't have to prove that because I have something much stronger than a proof. That's a directly observed fact.
Well, the conformity of the Earth to a sphere is not directly observable. It's very difficult to work out. Some people are aware that the poles are, for example, wider than the North Pole. I doubt you could even describe how to work that out, much less. I don't think you could work that out if I gave you $1 million. I don't know what you'd do. Would you hire an airplane? What would you do if you had a million
Yeah,
dollars to actually measure the
it's
shape of the Earth?
true that well, you're certainly, it's a directly observed fact that the Earth doesn't bulge out anywhere by 100 miles, right? I mean, we can take pictures of the Earth from, you know, from geosynchronous orbit or anywhere else and prove by direct observation. I shouldn't have said proof. We can directly observe the fact that the Earth does not bulge out anywhere by 100 miles, maybe 10 miles, probably a mile, bulging out if you localize that. But once again, I mean, I think it's really important to understand that there are directly observed facts. They're used to generate more general models, and then those models have entailments in the form of other things that should be directly observed facts, which we then go out and see if they are.